When we encounter a function like x raised to the power of x, we face a unique challenge. Unlike standard power functions or exponential functions, both the base and the exponent are variables. This means our basic differentiation rules won't work directly on this expression. Our objective is to find the derivative, dy or dx, which represents the instantaneous rate of change or the slope of the tangent line at any point along this curve. Let's walk through the mathematical steps to achieve this. We begin by taking the natural logarithm of both sides of our equation. This is a mathematically sound move as long as x is positive, and it sets the stage for using the power property of logarithms. Now, we apply the power rule for logarithms. The exponent x inside the log moves to the front as a multiplier. Our equation is now ln of y equals x times the natural log of x. This is much easier to differentiate. Next, we differentiate both sides with respect to x. Because y is a function of x, we must use implicit differentiation on the left side. This means we treat y as an inner function within the natural log. The derivative of ln u is 1 u times u prime. Therefore, the derivative of ln y with respect to x becomes 1 over y, multiplied by the derivative of y with respect to x, which we write as dy or dx. On the right side, we have a product of two functions x and ln x. We must apply the product rule, which states that the derivative of a product is the derivative of the first times the second, plus the first times the derivative of the second. The derivative of x is 1, so the first term is 1 times ln x. The derivative of ln x is 1 over x, so the second term is x times 1 over x. Notice how the x and 1 over x will cancel out. After simplifying, the right side of our equation becomes simply the natural log of x plus 1. We have successfully differentiated the product, and now we are ready to combine both sides of our equation again. We now have the full differentiated equation, 1 over y times dy or dx equals ln x plus 1. To find the final derivative, we need to isolate dy or dx by moving the 1 over y term to the other side. By multiplying both sides of the equation by y, we isolate dy or dx. The derivative is equal to the original function y multiplied by the quantity natural log of x plus 1. We are almost at the final form. Since we want our final answer in terms of x, we substitute the original expression for y back into the equation. Replacing y with x to the power of x gives us the complete derivative x to the x times ln x plus 1. Let's test this. At x equals 1, the value of the function is 1. Plugging these into our derivative formula, we get 1 to the power of 1 times the natural log of 1 plus 1. This simplifies to a slope of exactly 1. At x equals 2, the slope is 4 times the quantity lane 2 plus 1, which is approximately 6.77. This demonstrates how quickly the function x to the x grows and how its steepness increases as x moves to the right. To summarize, logarithmic differentiation involves 5 key steps: taking the log, simplifying with log properties, differentiating both sides implicitly, isolating the derivative, and substituting the original function back in. This technique is essential for variable bases and exponents. Quick question: what is the first step to differentiate y equals sine of x to the power of x? If you said take the natural log of both sides, you're correct. This method works for any function where the exponent is a variable. Generated by Vision Solve AI.